In this video, we're going to look at some identities and some equations that involve the application of multiple angle identities. In this first example, we're given an identity. We're asked to verify that it is an identity. And with identities, what I like to do is draw a wall under that equal sign to remind myself I can't move things from side to side. I'm just trying to show that both sides are equal. I'm going to start over here on the left side. I have sine 2x. And that 2x tells me I need to use a double identity, a double angle identity. So I'm going to change sine 2x to be 2 sine x cosine x because that's my double angle identity. And then that's still divided by tangent x. Now I'm going to change tangent x to sine over cosine. So 2 sine x cosine x divided by sine x over cosine x. And now I'm dividing with fractions, and so I'm going to change this to multiply by the reciprocal, 2 sine x cosine x over 1, if you want to have that as a fraction, times the reciprocal of sine over cosine, which would be cosine x over sine x. Now I have a sine x in the numerator and the denominator, so I can cancel those out. And what I have left is, run out of room, run out of screen here, 2 cosine squared x, which matches my other side. And so I verified the identity. Let's look at another example. Here I have cosine to the 4th theta minus sine to the 4th theta equals cosine 2 theta. It does say verify the identity, so I'm going to put up my wall. And cosine 2 theta, that indicates that I need to use a double angle identity. But if you remember, there's 3 different versions of the double angle identity for cosine. And since I'm not really sure which one to choose yet, I'm going to start working on the left side. I have cosine to the 4th minus sine to the 4th. That is a difference of 2 square terms, and so I can factor that. And I'm going to make it cosine squared theta plus sine squared theta and cosine squared theta minus sine squared theta. So now if I consider what I have, I've got cosine squared plus sine squared. Well, that's a Pythagorean identity. Cosine squared plus sine squared is equal to 1. So I'm going to change that to 1. And then I have cosine squared minus sine squared, which, if you look at your double angle identities for cosine 2 theta, that happens to be one of the representations of that identity. This is equal to cosine 2 theta. And so we have verified that identity. All right, in this next example, we're actually going to be solving an equation that involves one of these double angle identities. Cosine 2 theta. Now again, this is the double angle identity that has 3 different representations. But here, I know that I'm going to choose the one that involves sine because the other term here in my equation is a sine theta. So I'm going to change cosine 2 theta to be 1 minus 2 sine squared theta minus sine theta equals 0. So now I have my equation all in terms of one trig function, which is what we prefer whenever we're solving trig equations. Now I notice that I have a squared, I have an exponent, and that means in order to solve this equation, I'm going to need to factor. And if I'm going to factor, I need one side equal to 0, which we already have that. But personally, I like my square term to be positive. And so I'm going to move all of these terms over to the other side so I can change their signs. So I would end up with 2 sine squared theta plus sine theta minus 1. So now I have this in terms that I'm ready to factor. Now remember, if you're still having trouble factoring trig functions, you could rewrite this as 0 equals 2x squared plus x minus 1. And then do your factoring just in terms of x, and then change it back to sine. But I'm going to go ahead and continue working with the trig function. So if I factor this, I'm looking at 2 sine squared theta first, and I'm thinking, what can I multiply together to get 2 sine squared theta? Well, my only choices are 2 sine theta and sine theta. And then I look at my last term, 1. What can I multiply to get 1? Well, my only choice is 1 and 1. I need it to be negative, though, so my signs are going to be different. And now I look to my middle term. I want to have plus sine x in the middle. So that means that I need to get a positive here and a negative here, so that when I multiply these 2 terms together, I get 2 sine theta. When I multiply these together, I get negative sine theta, negative 1 sine theta, if you want to put a 1 in front of it. And then if I combine those 2 terms together, that would give me the plus sine theta in the middle. All right, so I'm going to get rid of all of that extra stuff I just wrote. And now we're ready to set each part of this equal to 0. 0 is equal to 2 sine theta minus 1, or 0 equals sine theta plus 1. So over here on the left, if I solve this for sine theta, I get sine theta is equal to 1 divided by 2, 1/2. And now I'm choosing angles from my unit circle. Notice in our directions it said to solve the equation on the interval 0 to 2 pi. And so I know that sine is 1/2 whenever my angle is a pi over 6 angle. Sine is also 1/2, noting that this is positive. Sine is also positive 1/2 in quadrant 2. And so that pi over 6 angle in quadrant 2 is 5 pi over 6. So there's those solutions. Now I'm going to go solve this other equation. If I subtract 1 from both sides, sine theta equals negative 1. And that happens when theta is 3 pi over 2. And so those are our solutions to that equation. Very similar to solving other trig equations. The main difference here was this first step where I had to substitute in a double angle identity. All right, let's look at another equation. Again, we're solving over the interval 0 to 2 pi. We're going to start this out like I did the previous question. I have sine 2 theta. So I'm going to substitute in that double angle identity for sine, which is 2 sine theta cosine theta. And then I still have minus sine theta equal to 0. Now here I've got an equation that has 2 trig functions in it, a sine and a cosine. And remember that normally when we're solving equations, we like to have them in terms of only one trig function. But that's not always possible. And this is an example of when that's not possible. There's no way for me to change sine to become cosine. And so I need to work with what I have here. I have 2 terms, 2 sine theta cosine theta and sine theta, and they both have a sine theta, so I can factor that out. Sine theta, bring it out to the front, and if I do that in my first term, I'm left with 2 times cosine theta minus, and then if I factor sine theta out of my second term, I'm just left with 1. And this is still equal to 0. So now I'm factored, ready to set both parts equal to 0. Sine theta equals 0, or 2 cosine theta minus 1 equals 0. Well, sine theta equals 0 whenever theta is 0 and pi. Remember, sine corresponds to the y-coordinate on the x-axis, and the y would be 0. I'm sorry, sine corresponds to the y-coordinate on the unit circle, and the y-coordinate would be 0 whenever we're on the x-axis. So that would be at the angles 0 and pi. In my other equation, cosine theta would be equal to 1/2, and that happens when theta is equal to pi over 3 in the first quadrant, and then cosine is also positive in quadrant 4, and so I need that pi over 3 angle from quadrant 4, and it's going to be 5 pi over 3. And so those are my solutions to this equation. Let's look at another type of example. In this example, we're asked to solve this equation on the interval 0, 2 pi, but we have tangent is equal to tangent of 4x is equal to 1. Now I don't have a quadruple angle identity, and I suppose I could use a double angle identity twice, but there's really a simpler way to think about solving this. If I let me get a different color for this. I'm going to say let theta equal 4x. And then I'm going to rewrite my equation. And instead of 4x, I'm going to put theta equal to 1. That's an equation I can solve. Tangent theta equal to 1. Remember that tangent is slope, and my slope is going to be positive 1 whenever theta is pi over 4 or 5 pi over 4. Tangent is positive in quadrants 1 and 3. But these aren't going to be my only possibilities for theta, and here's why. I was given the interval 0 to 2 pi, but this interval 0 and 2 pi, those are x numbers. Those represent x's for my original equation. And I'm solving in an equation that involves theta, and I've said that theta is equal to 4x. So if this is my interval for x, then my interval for theta is going to be 0 to 8 pi, because theta is equal to 4 times x. And so what I have here, when I've got pi over 4 and 5 pi over 4, those are my solutions between 0 and 2 pi, but I need to get more solutions. So let's think about what this looks like. Pi over 4 and 5 pi over 4. That would be these angles right here. Pi over 4. Let's use different colors. This would be pi over 4. And I'm going to do this one in green. This would be 5 pi over 4. Now I could, if I just want between 0 and 8 pi, then let's just start with the pi over 4 angle. That means that I could go all the way around and back to the pi over 4 angle to get a coterminal angle that would be 9 pi over 4. And I get that by adding 2 pi. Pi over 4 plus 2 pi would be 9 pi over 4. I'm going to likewise add 2 pi to the 5 pi over 4. So 5 pi over 4 plus 2 pi would be 13 pi over 4. So now if I've added 2 pi once, this means that I've got my choices between 0 and 4 pi, but I still need to go all the way out to 8 pi. So I'm going to add 2 pi again to both of those and get 17 pi over 4 and 21 pi over 4. So now I've gone up through 6 pi. So I need to do this one more time. 25 pi over 4 and 29 pi over 4. And that finally gets me up to 8 pi. Notice that I started out with 2 solutions between 0 and 2 pi, and then I got 2 more solutions to get me up to 4 pi, 2 more to get me up to 6 pi, and the last 2 to get me up to 8 pi. All right, so these are all of my possibilities for theta. But remember, I'm actually solving for x, and theta is equal to 4x. And so that means for each of these equations, for each of these angles, what I'm going to do is say 4x equals, and let's just start with the first one, pi over 4. And so to solve that for x, I need to divide by 4. And so x would be pi over 16. And likewise, with all of the other angles, I'm going to divide them all by 4. And what happens when we divide by 4 is that we actually end up multiplying by 4 in the denominator. And so I'm just going to rewrite my answers. I'm going to erase that example since I'm running out of room here on my screen. X is equal to pi over 16, which was my first answer, 5 pi over 16, 9 pi over 16, 13 pi over 16, 17 pi over 16, 21 pi over 16, 25 pi over 16, and 29 pi over 16. So pretty crazy, a little bit different than the problems that we had done before, but that gets us all of our possible solutions. Let's look at one more example that would be like this one. Here we have 4 sine squared of 2x minus 3. Now I could substitute in the double angle identity, but then it's being squared, and so that's going to make it a little bit more complex. And also, if you remember, my double angle identity for sine is 2 sine x times cosine x. But I have this 3 here, this term of 3 that doesn't have a sine or cosine with it, and so I wouldn't be able to factor one of those out and make it possible to solve. So I really can't use the double angle identity in this case. And so I'm going to go ahead and solve for sine 2x. So I'm going to add 3 to the other side. 4 sine squared 2x equals 3. And then I'm going to divide by 4. Sine squared 2x is equal to 3/4. And then I'm going to square root both sides. But don't forget that when you square root both sides of an equation, you have to remember to put plus or minus square root of 3/4, which is actually plus or minus the square root of 3 over 2, because the square root of 4 is 2. All right, so now I have this equation. Let me just rewrite where we are here. Sine of 2x is equal to positive or negative square root of 3 over 2. Now that's something I could solve if it was just sine x, but it's sine 2x. And so here's where we're going to say, let theta equal 2x. And then I'm going to rewrite the equation as sine of theta is equal to, sorry, let me try that again. Sine theta equals positive or negative square root of 3 over 2. But let's remember the issue with our interval. Remember that the given interval, I'm starting with an x interval of 0 to 2 pi. But theta is equal to 2 times x, and so my theta interval is going to be 0 to 4 pi. So I need to get all the angles between 0 and 4 pi for which sine of theta is equal to positive or negative square root of 3 over 2. So let's see if we can start listing those angles. I'm going to get a new screen for this. Whoops. Sorry, a little technical difficulty there. All right. Sine of theta equals plus or minus square root of 3 over 2. On the interval, the theta interval, 0 to 4 pi. Well, I know that sine is square root of 3 over 2 whenever the angle is pi over 3. And since it's plus or minus, I'm going to get the pi over 3 angle in every quadrant. 2 pi over 3, 4 pi over 3, and 5 pi over 3. So that gives me 4 answers between 0 and 2 pi, but I need to go all the way out to 4 pi. So I need to find those coterminal angles between 2 pi and 4 pi. So what I'm going to do is add 2 pi to each of these answers that I already have. If I add 2 pi to pi over 3, then I get 7 pi over 3. If I add 2 pi to 2 pi over 3, I get 8 pi over 3. If I add 2 pi to 4 pi over 3, we get 10 pi over 3. And finally, if I add 2 pi to 5 pi over 3, then we get 11 pi over 3. And that gets me all of my choices between 0 and 4 pi. Now I need to convert these back to x numbers to get my final answers. Remember from the previous screen that we let 2x equal theta. So that means that each of these thetas is going to be equal to 2x. So I'm going to start with the first one. 2x is equal to pi over 3. And then to solve for x, I'm going to divide by 2, which is actually the same as multiplying by 1/2. And so I get pi over 6. And I'm going to do the same thing to all of my answer choices there. Dividing everything by 2, which is really the same thing as multiplying by 1/2. And so my answers are x is equal to pi over 6, 2 pi over 6, 4 pi over 6, 5 pi over 6, 7 pi over 6, 8 pi over 6, 10 pi over 6, and 11 pi over 6. Now, of course, some of those could be reduced, but you get the idea, hopefully, of how we change between those two different variables.